So now let's look at a second case. What if we're not so lucky? What if the state that we're dealing with is a mixed state? In other words, there are different possible values when we try to find the measurement for an observable A. Now what? Well, in that case, I cannot say there's a single possible measurement result anymore, but at least I can ask, for example, what is the average measurement value? Suppose you did 1,000,000 measurements under the same state. You average all these 1,000,000 measurements. What are you going to get? This is called the average value, of course. In quantum mechanics, we also give it a special term. We call it expectation value. Okay, we use the symbol. This is a symbol we often use. We also use this symbol quite a lot. This means the same thing. It is really just the mean value, okay, of this. If you take a whole bunch of measurements, you average them, that's what you're going to get. If I have a mixed state, psi, okay, and I want to know what kind of expectation value I'll be getting if I try to measure a quantity A, what am I going to do? Well, we know that this A measurement will be sharp, will be unique only when it's with a pure state. We do not have a pure state right now. However, I can decompose this psi into a whole bunch of pure states for this variable A. So psi 1, psi 2, psi 3 each is defined to be a pure state of the variable A, such that A operating on psi n equals a constant an operating on psi n. Okay, so basically the idea is we decompose any mixed state into a bunch of pure states. There's a coefficient Cn here. The larger that coefficient, more likely you're going to find our measurement to be in this particular state, whose value is A of n. Okay, an example of decomposing a mixed wave into pure waves, pure states, is something we already saw before. This is a mixture of two simple harmonic waves, one traveling to the left, one traveling to the right. So they're both, each of them is a pure state of momentum, but you mix them together, it's a standing wave, it's no longer a pure state. We can mix it together, we can decompose it into a left traveling wave and a right traveling wave, right? Using Euler's formula. Okay, so that is an example how we do that. Suppose we did that, okay? Now, you have a whole bunch of terms. Let's say you have 100 possible values of A, and therefore there are 100 terms here for 100 pure states, okay? But you still have to satisfy what's called normalization condition, and that is when you sum over the entire probability of finding this particle everywhere in space, assuming it's only in the x direction for simplicity, okay? This psi star psi is the same as psi squared. Psi star psi is the same as modulus squared, right? Because this is, this is how complex variables tell us. So I'm going to do this, psi star psi dx. I'm going to integrate over the entire space. Okay, I require the answer eventually to be 1. Now let's see what we get. This is the sum, and so is that. So here's the sum for psi star, and here's the sum for psi, okay? I do not want to mix the indices, so I call this index, I call it m for this psi star, and here the index, I call it n for psi. So m and n can be independent. They're independent, okay? So cm star, psi, m star, and so on. Now, I'm going to do the integral now. Cm star and Cn, both are constants independent of x, so I'm going to take these out. What's left for integration is psi m star and psi n. Both of these are functions of x. Okay, so I have to integrate. Now here's the thing. When I integrate this, what do I get? Suppose m and n are the same. That means I'm talking about the same quantums, the same eigenstate with this eigenvalue of n, right? Then this is really just psi n modulus squared integrating over the entire space. By definition, I should get 1 because each state, each eigenstate itself is normalized. So that's just 1 if m equals n, right? Now the tricky part is what if m not equals to n? So we're looking at two different eigenstates of the same variable corresponding to different eigenvalues. Okay, what is that equal to? Well, it turns out that is when the integral equals 0. So in mathematics, we say these two states are orthogonal to each other. these two vectors are orthogonal to each other. And I'm not going to prove it here for you, but trust me, this is true. And you can see in our examples later, all of those examples, this is actually true. Okay, so we say in general, this is equal to the so-called Kronecker delta, which is defined to be equal to 1 when m and n are the same, and 0 when m and n are different. Okay, so this double sum, in fact, becomes a single sum because m cannot be just anything. It has to equal to n, otherwise the sum is 0. So we just have to sum over n. When m becomes n, that is the only time when it's the term is not 0. So I replace m with n. You see that? Okay, and what's left is this integral, which in this case is just 1, right? Because m equals n. And this really, Cn star Cn is just the modulus squared of Cn. You integrate, you add through all n, you get 1. Because by definition, the eventual answer is 1. So you basically add C1 squared and then C2 squared and blah, blah, blah. You always get 1, no matter what that function, the initial wave function is. When is that always equal to 1? It's because this Cn squared is nothing else but the probability of finding the system, our particle, to be in such a state, such an eigenstate of A, in the nth eigenstate of A. So in that state, its value, the value of this operator would, of this observable would be A of n. You know, see that. Now, this particle may be in 100 possible states, eigenstates. Suppose there are 100 possible values for this observable A. So there are 100 eigenstates, right? It can be any 100 states, but the probability of finding the particle in the first state, second state, all the way to 100 state, you add them all together, what do you get? You get 1, don't you? That is normalization, because there are only 100 possible values for this observable A. It's going to be one of these 100 values, right? So it makes sense that this really is Pn, okay, Pn. The probability of finding our system with this mixed state to be in one of the pure states. And the reason why you cannot pinpoint where the exact measurement would yield is because you do not know which one of these 100 pure states you're going to find this particle to be in the next moment. It hops between different states. For example, in this standing wave case, 50% of the time it's in this pure state. The next 50% of the time is in that pure state. You never know when the next measurement will yield in either of these pure states. But it's got to be in one of these two pure states. Okay. Now we know the value of this part of this observable if it's in one of the pure states, and the probability of finding this particle in such a pure state is P of n. Then isn't it true that the mean value of finding this particle in such a mixed state is just P1 times A1 plus P2 times A2 and so on? P1 is the probability of finding the particle to be in state 1, and in state 1 its value is A1, right? And in state 2 is A2 and so on. So it should be P1 times A1 plus P2 plus A times A2 and so on, right? And Pn is just Cn squared. So you see, even for a mixed state, we will be, at least in theory, we can find the expectation value or the mean value. All we have to do is to decompose this, okay, our state, into a bunch of pure states of this particular variable. So we can find C1, C2, C3, and so on. And then we take the C1 squared, C2 squared, C3 squared, multiplied by its corresponding pure or eigenvalue in this particular state, and add them all together, I get what I want. Sounds complicated, but at least in theory, that is what we can do. Okay? Let's look at an example. Using the standing wave, again, as an example. This standing wave, the time-dependent part e to the negative eigenvalue t, I don't really care that much. The space-dependent part is sine kx. Again, I break it down into e to the ikx and e to the negative ikx. Okay, so here's a forward traveling wave. Here's a backward traveling wave. So the system, 50% of the time is traveling this way, positive k. Another 50% of the time you find the particle going backwards, negative k. Okay, it can be just bouncing back and forth between two walls. Now, in this case, the coefficient in front of this pure function and in front of that pure function, they're equal to each other. I mean, forget about the negative sign because I'm just talking about the magnitude. Okay, so c plus k, that's the coefficient here. C minus k is the coefficient there. they have the same magnitude, but the modulus square should add up to 1 because that is normalization condition, and therefore each of these modulus squared must equal to 1/2, right? Because they add up to 1, they're equal. So what is the k value? The mean expectation value of the wave vector k. Isn't it equal to the probability of finding it to be positive k times positive k plus the probability of finding it to be negative k times negative k, right? There are only two possibilities, right? And each of these is 1/2, right? 50% of time here, 50% of time there. So 1/2 times k plus 1/2 times negative k, and that's 0. So according to our calculation, the chance of what is the expectation value of the wave vector in this mixed state. In other words, when you measure its wave vector a whole bunch of times, you add them all together, you should get 0. That makes sense. That makes perfect sense because, again, 50% of the time k has a positive value, 50% of the time has a negative value. They have the same magnitude. Of course, you should add up to 0 when you do a whole bunch of measurements. Okay. Correspondingly, px, which is proportional to k, that's also 0. So the momentum has no preferable direction. The average value is 0. Okay. What about the kinetic energy? Well, the kinetic energy is px squared over 2m. Now, px squared average value is not the same as px average and then squared. Okay. You have to square it first before you take the average instead of averaging it first and then you take squared. It's not the same thing. And this px squared is h bar squared k squared. So you have to average over k squared. So let's see how we can average over k squared. Now there are two possible k values, positive k and negative k, each with a probability of 1/2 and 1/2, right? So there's a constant here, and then we start to do the k average. This is k average, okay? Actually k squared average. 50% of the time it's got positive k squared. The other 50% of the time it's got negative k squared. Now the negative doesn't really matter because you square it. You add them together, you just get k squared. This whole thing is just equal to k squared. And that's what you get, h bar squared k squared over 2m. That's the same as p squared over 2m. So clearly, we also get the correct value for the kinetic energy expectation value. In fact, kinetic energy is not, you don't just calculate expectation value. This is the only value you're going to get, okay, which is equal to expectation value, of course. So with all this calculation, we established, at least in theory, how we can find the expectation value of any observable, even in a mixed state. But it is not always a convenient thing to decompose a wave into a whole bunch of pure states for a given variable. Okay, we did that. We used a very simple example. This is easy to do. But can we possibly find the expectation value of a certain physical observable A without going through the decomposition process? Can we do that? Well, it turns out there is a way to do that. You do not have to decompose the wave function into a bunch of pure waves for a given variable. You can simply use the operator associated with that variable A, observable A. You can still find the expectation value, and we will see how we can do that. And it turns out we can do that by using the operator in association with that observable A. Remember, we define an operator in association with any observable, and once you define that operator for that observable, I want you to consider this following expression: the integral of psi star A, operator A, operating on psi dx. Okay, psi star is in front of it. You do not operate on psi star, you operate on psi. Let us see what this will give us. Okay, I want you to show that the expectation value of A, which of course is given by this, right? P1 A1 plus P2 A2 and so on, and P1 is the probability to find this particle to be in pure state number 1, and so on and so forth. Pn is Cn squared. We saw that before, and we want to show that this average value, expectation value, is equal to our expression right here. So you know, without decomposing it, I don't have to decompose it. I just take this integral, and I get what I want. Let me show you how we can do that. Okay. Now we are not going to actually decompose it, but let's pretend we did. Okay. So we decompose psi into a bunch of pure states like we did before, and psi star therefore is just Cn star, Cm star psi m. I have to integrate. I have to sum over the same possible values, but I use a different dummy variable m instead of n. And then I plug both of these into here. Okay, so this is the sum. That is also a sum. And this is what I get. Okay, psi star is right here. A is in the middle. And psi is right there, right? There are two sums. One psi star, one psi. Now, the operator A in the middle, it operates on this bunch of sums. Cn is a constant, so the operator bypasses this constant, and it's working directly on psi n. Now remember, psi n is an eigenstate, eigenfunction of the operator A, and therefore A operating on psi n equals just an, a number, times psi n, right? So this is what we're going to do. We plug that result into here, and let's see what we get next stage. Okay, we copy this, and this time A operating on psi n becomes an psi n as we used this expression. Okay, now one more step. I'm going to take all the constants out. Cm star, Cn, An, these are just constants, right? What's left is the only integrating part is psi m star and psi n, because these are dependent on x. I have to integrate. But what exactly am I getting? Isn't that the Kronecker delta mn? So again, this integral is only non-zero when m equals n, which reduces this double sum into a single sum over n, and when m is equal to n, this integral equals 1 by normalization, so I get this, Cn star, Cn, An. And this, as you recall, is just Cn star, An. That is exactly what I try to prove. Okay, so I do not really have to really decompose this wave function into a bunch of pure state wave functions. I just find the corresponding differential operator. I need to know that, very important. Then I just do this integral. I will find the expectation value of any observable A, even in a mixed state. So here is how we summarize what we got. What is it that we can get from the wave function? Well, you solve the Schrödinger's equation, you get the wave function, right? And at the same time, we need to define an operator in association with an observable A. How do we know anything about A? Well, it depends on whether it's a pure state or not. If it's a pure state, we can find the only possible value of that observable for a pure state or eigenstate. All I have to do is to take that operator operating on a pure state, whatever constant we get out of it, that is its value. You're always going to find the exact same value no matter when, no matter what. And another case, if you have a mixed state, we cannot find its only value because there's more than one only value, but we can find the expectation value. How do you find expectation value? As we saw in a previous discussion, it's just this integral. You do not have to decompose it into psi 1, psi 2, and so on. Just integral tells you what the expectation value is. But suppose you did decompose it. Suppose you took the trouble and did that. Okay, C1 psi 1 plus C2 psi 2 and so on. What can we extract from this decomposition? You can not only find the expectation value of this quantity, you can also find how likely can you find this state, our particle, to be in state number 1 or state number 2 or state number 3 and so on. And each of the state, again, is a pure state of the observable A. So we know a lot about our system from the Schrödinger's equation. We know everything. Again, we have the right to know about the system. So then you might ask, what do you mean by something we have the right to know? How do we know that we have the right to know this, but we don't have the right to know that? Right? For example, you know we do not have the right to ask the exact value of both px and x at the same moment. But what about px and y, not px and x? Can we find in principle px and y with 100% accuracy simultaneously? Those are the things we'll be discussing. It has to do with the root behind the uncertainty principle. In fact, we'll be using the idea of the so-called simultaneous eigenstates and the idea of so-called quantum commutators to figure out what is it that we can find exactly, what is it we cannot find exactly. And that will be in our next lecture.